Okay, so welcome to another session which we are calling analysis of variance, and this is supposed to be session 12, not necessarily session 5. And in analysis of variance, we are just continuing with how we test hypothesis. This time, not for just two groups, but for more than two groups. So, how do we do this, and how do we test for such hypothesis? And that is what we are interested in. So, basically, analysis of variance is interesting, and it's one that also holds a lot of practical implications. And based on what we want to do, we can use analysis of variance to do it. And trust me, most of you will end up using that in your various research works as you progress academically. All right. So in the previous session, what we were doing was basically comparing means, average values between two groups, right? And this time, we're going to go beyond two groups, okay, comparing mean for two groups. I'm going to look at comparing average values or means for three or even more independent groups, okay. And that is where analysis of variance come in. So after completing this session, this is what you should be able to do. Number one, you should be able to recognize situations in which we are going to use analysis of variance, right? Number two, you would also learn how to understand different analysis of variance designs. Number three, you would understand how to perform a single factor analysis test and hypothesis test and interpret the results. Conduct and interpret analysis of variance, pairwise comparison procedures. And if there's time, you would analyze two-factor Anova with replications. Okay. All right. Your recommended text, I hope you are reading. Okay, so what is Anova? What is analysis of variance? It is a technique that is used to test the differences in the means of more than two populations. Okay, and mostly we want to ensure that these assumptions are met, that populations are normally distributed, populations have the same variance, and the population variances are equal, and the sample observations are different. Okay, so the level of measurement is interval or ratio. Okay, so what are we really trying to do? Okay, we are trying to ensure and measure and test hypotheses between three groups. In the first instance, we were looking at the situation. I think I gave this example about accounting and finance, whether you were testing whether accounting students perform better than the finance students and so on and so forth. Now, we are interested in the third group, okay? We are interested in whether, let's say that accounting, finance, and marketing, okay, they have the same means, or one performs better than the other, or one performs worse than the other, or their performances are equal. Okay. So in doing this, we are going to use a different approach in solving this. Now, we are going to rely on variation, okay, rather than differences in means. Okay, so we are going to look at whether the variation, and we will explain this as we move on. If the variation among the sample is small, then it supports our hypothesis of equality. If there's so much variations among the groups, then it actually leads to against the null hypothesis. We would look at that, or it supports the alternate hypothesis. we'll go deep into that. Okay, so we normally use Anova in most of our experimental designs, especially in agriculture, where they test various results at various treatment levels. But of course, we are going to use it a bit differently, but with the same mindset. Okay, but with the same approach. Okay, we've already talked about the assumptions that we're going to use. Okay, populations are normally distributed. Populations have equal variances. The samples are randomly and independently drawn. So basically, the analysis of variance is going to test whether there's difference among three or more populations. So, for example, accident rates for third, first, and then second shifts, and or whether there's a difference between the mileage of for brands of 5 ties. Yeah, can anybody give us any real world situation that can warrant an analysis of variance test? Is there anyone who have thought of anything that we think will warrant an analysis of variance test? Yeah, you can put the answer in the chat box, or you can just raise your hand and then I'll call you if you have such an example in mind. Okay, so while we are waiting for such examples, we'll move on with what we have. Okay. So there are several approaches to several techniques, even within the analysis of variance framework. But we are going to consider what we call a single factor analysis of variance. Okay, and we are going to consider what we also term as the one factor Anova or the one-way Anova. Okay. Now, if all the groups or what we call factor levels, or yeah, the groups have the same sample size, we call it a balanced design. If the sample sizes are different, then we call it an unbalanced design. So there's no one who can give us any example of analysis of variance. Okay, we move on to what we are doing. All right, so let's come back to a situation we have here, and um, Othniel, different learning methods leading to different exam scores. Um, yeah, but that was quite broad. But I think I need you to unmute so that you can lead me, or you can help me with the examples that I want to give. Othniel, how are you?
Pardon?
How are you?
I'm fine, sir.
Great. Okay, so let's take into consideration. Let's take, for instance, we have three groups of classes. Okay, so let's say group one, accounting, right? Group two, marketing, and then group three, finance, right? And of course, we are going to use mu1, mu2, and mu3 for their groups. So we want to test whether the performance, okay, and this doesn't go for Othniel alone, but it goes for all of you. We want to test for the performance of these people, whether there's a difference in their performance, right? Whether there's a difference in their performance. Assuming that the average score for group one is mu1, okay, mu1, then group two is mu2, and then group three is mu3. Okay, Othniel, how would the null hypothesis be formulated? What do you think would be the null hypothesis?
I was paying attention, sir.
Sorry?
I didn't get the question. I wasn't paying attention.
I said, how will the null hypothesis be formulated given this, if you want to test whether there's a difference in their whether there's a difference in their performance?
Oh, in all three performances.
Yes.
Let's see if mu1 is equal to mu2, and if that's also equal to mu3.
Okay. So just hold on a bit for me. I'm writing. So you want to test whether
mu1 is
okay, hold on.
equal to mu2.
Equal to mu2, right? So mu1, then we have that here is equal to mu2. So we change it here, and then it's equal to mu3, right? How do we formulate the alternate hypothesis?
That is a good question.
Yeah, that's why I'm asking it. Okay. Okay, guys, I want you to also indicate it in the chat. How do you?
So we use the not equal to.
Let me pick a sample of alternate hypothesis. What's your
mu1 is not equal to
mu1 is not equal to mu2,
equal to mu3.
and it's not equal to mu3. Okay. All right. Yes. Does anybody have a contrasting viewpoint as regards to this? All right, Otna, thank you. Right.
You're welcome, sir.
All right. Does anybody have any other contrasting viewpoints that you think is, or everybody thinks this is what it should be? Yeah, you can raise your hand, or you can tell me. Okay. Okay, Emmanuel has given me so many things. Emmanuel, choose one. Which is which? This is what Emmanuel is saying. Mu1 is not equal to mu2, and it's not equal to mu3. Mu1 is not equal to mu2, but mu2 is equal to mu3. Mu1 is equal to mu2, and mu2 is not equal to mu3. But I just want one statement that covers the alternate hypothesis. So how do I get that statement? Yes, anybody? Okay, Maureen.
I think we said that not all are the same. So whether it is the difference is between mu1 and mu2 and mu3, or mu1 and mu3, they are not the same. Not all the populations are the same. Means are the same.
Exactly. I mean, that is it. So our alternate hypothesis is that not all of the population means are the same. Okay. Now, because and Iman, you are right here. The null hypothesis says that mu1, the three groups are the same, right? So anything that doesn't hold, okay, that provides a counterexample or a different format that goes against the null hypothesis. Okay, it's just like me making a general statement by saying, okay, and apologies if you wear glasses. If I make a general statement and I say all those who wear glasses are sharks, okay, all those who wear glasses are the best performers in class. Now, if I make such a case and you are able to find one person who wears glasses and is not so good in class, then you'll be able to refute my claim, isn't it? So anything that really goes against or contradicts what we have stated here in the null hypothesis goes in favor of the alternate hypothesis. So it can be that the first group mean will not be the same as the second group mean, and will not be the same as the third group mean. It can also be that the first and the second are the same, but the second and the third are not. It can be that the first and the third are the same, but the second and the third are not. It can be that the second and the third are the same, but the first and the second are not. It can be a whole lot of things. And it even gets worse when we have so many groups, 4 or 5 groups. Okay. So in all this, all you are expecting to see is that at least one of them should be different. Okay, at least one of the groups should be different, or at least one, not all of them are the same. So it's either not all of them are the same, or at least one of them is different. Okay, now if you want to be fancy mathematically, then we are interested in this. Our H alternate hypothesis can be written in this way. Instead of 1, I'll use I, a superscript, okay, and then I'll use J. So I'll say that AI is actually not equal to mu I is not equal to mu J. Mu I is not equal to mu J, basically, where I and J are just indices, okay, or indexes. It could be 1, 2, 3, 4, 5. So what we are saying is that mu1 at least, so at least mu I is not equal to mu J for I not equal to J. So you can use mathematical ways to write this, or you can even write them in words as it is written here. Not all the population means are the same. Okay, so don't be in a hurry to cross all equal to lines with to indicate a not equal to symbol. It doesn't really work like that here. Okay, we don't do that in Anova. But basically, it's just saying that at least one population mean is different, or there's a treatment effect, or it does not necessarily mean that all the population means are different. So there will be some pairs that are the same, but even when one deviates from it, okay, then that is it. That is like, yeah, we are done, like, basically. Okay, so we have that. So this is how we expect the null hypothesis to look like if it is true. Okay, if all the means are the same, then we expect that they all have the same average score. So you see that all the populations are normally distributed and they are centered around the same mean. So mu1, mu2, and mu3 are equal. All right. But if there are at least one is different, then you can have mu1 and mu2 being different, and then mu2 and mu3 being mu1 and mu2 being the same, but mu3 being different. Or you can have the three of them all different at the same time. Okay. All right. Now, if you look at the solution and the way we solve analysis of variance type of problems, we are basically interested in, as we said, as I initially indicated, although we are looking at the test of means, the approach to doing so is by looking at the variations. Okay, looking at the levels of variations. Now, the total variation that is existing and in the data that we have for the groups where we want to test their differences, okay, the total variation can be split into 2 forms of variation. Number 1 is the variations between the group, and then number 2 is the variations within the group. Okay, the variations between the group, which is measured by the sum of squares between. That's a numerical value. We call it sum of squares between, or between group sum of squares, or SSB, not a bank, but sum of squares between. Okay, And then the within group sum of squares, we term them as the sum of squares within. Some people call it the sum of squares due to sum of squares within. Basically, that is what we have. So in our analysis of variance, we are going to calculate the between group variations and the within group variation. Now, I want us to someone to help me with an illustration here. Yeah, let's have a conversation. Any volunteer so that we can have a conversation, just to enrich our understanding of the between group variations and then the within group variation. Okay, I'm not going to ask you what is 1 plus 1, so please, I want to see your hand up so that I can call you. All right. Nobody to volunteer to explain this. I'm not asking you to explain. Join me and let's explain together. Okay. Okay. Emmanuel, thanks. Let's start. Okay, Ima, what are the two main political parties in Ghana?
NDC and NPP.
Very good. Now, do they have the same ideologies? Hello?
Yes, please. No, they don't have the same ideologies.
So, between NDC and then MPP, there are two different parties, isn't it? Their ideologies are different. The way they think about things are different. So MEP brings one initiative or the other, NDC debunks it. NDC talks about one thing or the other, MPP debunks it. That's thing going on, right? Now, you can talk
Yes.
about, you can describe this as the level of variation that exists between them. So there is so much variation between NDC and then MPP as a group. Do you get it? But when you go into MPP
Right.
as a party, are there internal variations in the party? Internal differences, internal wars, and all that. Are there?
Yes, they are.
Like what?
For instance, maybe in drawing the manifesto or the budgets, maybe one person may say, oh, we should focus on this. The other person may say, no, let's do the other.
Yeah. But also, you can also talk about the fact that we even have you have the Alan group, you have the Baumia group, you have the Nanado group.
Yes.
Because in the run-up to any kind of elections, so there are internal issues within the party, although they are supposed to act as one. Okay, within the party, there are certain
as one. Yeah.
internal issues that needs to be resolved, isn't it? So we also so that is what the within group. So variation. So between two groups, there are variations.
Okay.
Right? Between two groups, between NDC and MPP, there are variations. But within the parties themselves, there are also variations. So much as NDC has the MPP has the Alan, the Alan group and the Baumia group and so on and so forth. NDC even have the Mahama group, the Spilgabra group, the Rolling Face, and you get it. So there are always internal level of variations within the party. Now, analysis of variance work in such a way that we acknowledge variances, we acknowledge variations that exist between groups, and we acknowledge variation that exists within a group. Now, if there are
Within.
yes, if there
Okay.
are differences, okay, of if the average score or the means of two different groups are significant, or three or more different groups should be significant, then there should be enough variations between them than within them. So we expect that there should be much differences between NDC and NPP than the variation that exists within NPP itself and within NDC itself.
Okay.
You get it?
Okay.
Because if
Yes, please.
there's so much differences or there's so much variations within a party, then the party could have as well divided itself. And that is why sometimes you have other political parties being formed out of some parties, right? Because their ideologies were so different that they couldn't stay in their party. Okay. So yes, we acknowledge differences.
All right.
We acknowledge all that. But for us to warrant and to make a case that NDC is significantly different from NPP, then the variations between the parties should be what? Bigger than the variations within each of the parties. So we are going to use those two words very carefully: between group variations and then within group variations. Okay, Ima, thank you. Thank you very much. All right. Now,
All right.
all right. Let's move. So what we are going to do is to find a way to calculate such variations, okay? The between group sum of squares and then the within group sum of squares. So I've explained this and I wouldn't want to explain it again. So as I said, the other names that are given to the sum of squares, of course, we can have sum of squares between, sum of squares among, sum of squares explained, among group variation. They are all ways you can call the SSB. And then also the SSW can also be known as sum of squares within, sum of squares error, the unexplained sum of squares, and then the within group variation. Yes, they can also have that. Now, let's do some mathematics. Okay. The total sum of squares is arguably, the sum of the between group and then the within group sum of squares. Okay. Now, we have k groups. Okay. K groups that we are dealing with, and each of the k has a sample size. So n1, n2, n3, n4, and so on and so forth. Now, in each of the population, there is a measurement or there are data that is found within each of the population. Then there's also a grand mean. If you want to find the between group variation, it is basically the difference, how each of the individual values vary from the mean. And in order to give an example, I want to use, how do you call it? I want to use some data to do it. Okay, so permission to use Excel once again. Yes, I promise that if after today I won't use Excel again. Okay, I can't promise that. Okay, so let's continue. Assuming you have three groups, number one, we talked about accounting. Number two, we talked about finance and marketing. And let's say that you have different samples and we've collected scores. So 5 different groups. So you have, let's say, yeah, these are the scores. And the finance, let's say we have this. I'm sorry if the scores are different. I randomly chose them. Okay. And then the marketing, no, that's too small. No. 7 here, 4 here, 1 there. Okay, now these are 3 distinct groups. Okay, so these are like 5 students in accounting, 5 students in finance, 5 students in marketing. We want to find a way, okay, of determining the total sum of squares. And the total sum of squares is this. Now, first of all, I can calculate, and I want you to pay attention here. I can calculate the averages, right? Averages. That is, I can calculate the average, the mean, the average for accounting, right? I can calculate the average for finance, average for finance, and then I can also calculate the average for marketing. Okay, so that is basically what we have. Now that we have been able to calculate the averages for the 3 groups, now I can also determine what we call the grand mean, right? The grand mean is basically the mean for all of them. Okay, so the grand mean, if I'm calculating the grand mean, I'm looking at the average of all the numbers irrespective of their position or irrespective of the group that they belong to. This is what we are terming as the X double bar or the X bar bar. Okay, in the determination of the X bar bar is just the mean of all the values, okay, or the grand mean or the mean of the means. If I take the mean of all of these, I get the same as what we have there. All right, so that is the now the total sum of squares measures how each of the individual values vary from the mean. Okay, how each of the individual values, these ones, how they vary from the grand mean. So basically, what it means is that it's like this. It's like this number minus this number. Of course, I would lock that one, then I square it. Okay, so that is the first one. The second one to the same thing. 4 minus 5 squared, that gives you 1. The third one, 7 minus 5, no, 5 minus 5 squared, that gives you 0. The fourth one, 7 minus 5 squared, that gives you 4. Then 3 minus 5 squared would also give us 4, right? So I can do same for all the values, right? And then yeah, so you see that this what we have here, right here, clearly is an expression of the total sum of squares, which is how each of the individual values, okay, vary from the grand mean. How each of these individual values vary from the grand mean. And of course, it is squared. So if I put them all together, okay, if I put them all together, then I get the total sum of squares. The total sum of squares. So that is how we calculate the total sum of squares. Now, so this is how we illustrate the total sum of squares. The red line is the grand mean. Okay, the red line is the grand mean. And these round items are the, the individual values. So you see that we are interested in finding how those individual values deviate from the grand mean for each group, how those individual values deviate from the grand mean. So if you are expanding from this notation that we use, beyond this sigma notation, can be expanded as this: x11 minus x bar bar, x12 minus x bar bar, as in the first number in the first group the second number in the first group, then the nth number in the kth group minus the grand mean. You square it, and that gives you, put them together, and that gives you the total sum of squares, like what we have here. Any questions before we move on? Okay. Now, the between group sum of squares is also identified as, and look at here, you see that it is x bar I minus x bar bar, and is weighted by the sample size. Okay, so basically what we are saying is that the sum of squares between is the mean, okay, the group mean, how the group mean deviates from the grand mean. So if I want my sum of squares between, I'll be interested. So this is my SST. Let's look at the SSB. I'll be interested in how this one deviates from the grand mean. Okay, how it deviates from the grand mean. Of course, I'll square it. Okay, I'll square it and I'll multiply by the sample size. What is the sample size for the first group? It is 5. Okay, so it's 5 multiplying this. Then we do same for the second one. You see, so this minus that, okay, all squared, then you multiply by 5. Then we do same for the third group also. We have 4.2 minus 5, then times 5. Of course, the difference, the deviation is squared. Now, if you put them together, what do you get? You get the expression for the SSB, the expression for the SSB, which is given as 8.4. So that is basically what we have for the SSB. The SSB is interested in identifying how each of the group means, individual group means, differ from the grand mean. How each of the individual group means will differ from the grand mean. Now, move on to the SSW. Okay, so we will talk about this later on. So for the SSB, you see that now each group has their own mean, x bar 1, x bar 2, x bar 3. So the SSB is measuring how that group mean would differ from the grand mean, how the group mean for group 2 differs from the grand mean, and how the group mean for group 3 differs from the grand mean. This is the expression for SSW, right? Who can help me with the interpretation for SSW? Who can help me with the interpretation for SSW? Who can help with the interpretation for SSW? Don't be scared of the mathematics and don't be annotating my screen if that is what you want to do. Okay. Who can give me an expression for SSW? Okay, Maureen. Yeah, Maureen, I'm listening. Yeah.
Okay, so I think it would be the variation within each group. So each individual value minus its mean. So for accounting, I think it would be
minus its mean, right? So how do we go through with this one?
I think accounting would be 5 minus 4.8.
We have
all
this,
squared.
okay, hold on.
Yeah.
We have this one minus
Mm.
8, right?
Yes.
Look, hold on. Very good. So we log that, and then we square it, right?
Yes.
Very good. So we do same for all the values, isn't it?
Yes.
Okay. And then let's go to finance.
So 7 minus 6.
So is this minus that, right?
Yeah.
And you raise to the power 2. So you have that running through it, right? So each item will be taken from its group mean, isn't it? Okay.
Yes.
Marketing.
5 minus 4.2 all squared.
4.2 all squared. So we have that. Then we okay. So when you're done, what do? You put them all together.
We have to put all of them together.
Okay. Very good. So that gives us an expression of the SSW, right? Now, Maureen, what do you think? The SSB plus the SSW should give us what? The SST, right? So what is 3.6 plus 8.4 should give us what? 52. If this doesn't work, then it means that our work would have been wrong. Maybe we'd have made a mistake somewhere if the SSB and then the SST were not the same. So what it also means is that you just need any two to get the other one. Okay, you just need any two to get the other one. Okay, so SSW, the variations within the groups, and we are looking at how each of the individual values differ from their respective means, right? Their respective means, and so on and so forth. So x1 1 minus x bar 1 squared, x1 2 minus x bar 2 squared, and so on and so forth. We have that. Once we have that, the sum of squares will help us to identify and draw what we term as the Anova table. Okay, the analysis of variance table. Now, this is a table that shows the results of the work that you have. Okay, so the analysis of variance has this as the headings. We have the sum of squares. Of course, we have the source of variation, and there are three sources of variation: the between group variation, the within group variation, and then the total variation. Okay, now we have the sum of squares, and under the sum of squares, you'll be calculating the sum of squares between, sum of squares within, and of course the total sum of squares. We have the degrees of freedom, okay, and that one too you'll be looking at. So for the sum of squares between, it has k minus 1 degree of freedom, where k is the number of populations or the number of groups. Okay, then the within sample gives us n minus k. That is the total big N. Big N is the total size of the data that you pick, and then of course the total will be big N minus 1. K minus 1 plus n minus k will give us big N minus 1. Now we calculate what we call the mean square. Okay, the mean square is like a variance or like a standard deviation that we deal with. So we divide the SSB by its degree of freedom, and then you get the mean square between. Divide SSW by its degree of freedom, and you get the mean square W. And you use this MSB and MSW to find what we call the F ratio. The F ratio. Now the F ratio is our test statistic. Okay, the F ratio is our test statistic. That is what we are going to compare with the critical value. Okay, so once we find the F ratio, So that gives us our test statistic. Then how do you find the critical value? The critical value will just be an F statistic. It has alpha, okay, and then the degree of freedom will be the numerator degree of freedom is k minus 1, and then the denominator degree of freedom is actually n minus k. So f alpha k minus 1 n minus k. This is what we are going to use as our critical value. So you compare. If the test statistic is greater than the critical value, then we are going to reject the null hypothesis. If it is not, then we will retain the null hypothesis. Okay, I think that is good. We can continue. All right, so let's take an example. Okay, if there are no questions, let's take an example. So we want to see if 3 different clubs yield. In fact, this one I won't ask for volunteers. I mean, the same people raising their hands, so I think we should just move on. Okay, you want to see if 3 different golf clubs yield different distances. So you randomly select 5 measurements from trials on an automated driving machine for each club. The question: at the 0.05 level of significance, test whether there's a significant difference in the average distance. So you have 3 different golf clubs, and each of these golf clubs are giving you different distances. What we are really interested in is whether there is a difference in the average distance traveled. Basically, we are asking whether the distance traveled by a golf ball, if the average golfer hits a ball with the same strength. Does it really depend on the club, the type of club that you use, or not? That is what we are going to we are looking. So we have 3 different clubs, 5 different samples for each club, and they yield different distances. Okay, so the question is whether there's a difference in the average distances. Okay, so club 1 has 254, 263, 241, 237, 251. I think that I'm going to put these values in the Excel that I created. Okay, then it would generate the value. So 254. So club 1, club 2, club 3. So we have 254, 263, 241. 237. So 254, 263, 241, 237. And then the last one is 251. Very good. Then club 2 has 234, 218, 235, 234, 218, 235, 227, 227, and 216. Then club 3, 200, 222, 197. So 200, 222, 197. And then 206 and 204. Okay, so we have that. And these are the averages. Let me see, 54, 63, 41, 37. Yeah, so X bar 1 is 249.2. X bar 2 is 226.0. X bar 3 is 205.8, as you can see, well calculated here. So we need this. And the grand mean X double bar is 227. Okay, all right. And of course, the sample sizes are 555 each. Your grand mean is 15, and your K is 3. Your K is 3. So we calculate the SSB, right? The sum of squares between is this 249 minus 227, as you indicated. The SSB is the difference between the individual means from the grand mean, and it is weighted by the sample size, right? Now here, because the sample size is the same, we can bring the 5 outside and then let's sum it across, multiply it through. Okay, so we have that 249.2 minus 227. Of course, most students forget the square. Please don't forget the square. 226 minus 227, 205 minus 227, all squared. That gives us our SSB 4716. Yeah, okay. 4716.4. That gives us the SSB of 4716.4, which is this. Then the SSW, we also have 254. Of course, note that it is each of the individual values, right, minus its group mean. Okay, minus its group mean. So this one takes the 249, the second group takes the 226, and the third group takes the 205.8. That gives us 1119.6. I don't need to calculate the SST, right? Because the SSB plus the SSW should give you the SST if your SSB and SSW are calculated correctly. Okay, then we can find the MSBs and the MSWs. So, of course, given this, we can draw our Anova table, right? So let's follow through with this same approach, and then we'll draw our Anova table. Michael, I will call you, but let me finish this one. So the source of variation, you have the between, you have the within, and then you have the total. We want to find the sum of squares. We have the mean squares, and then also, the degree of freedom, the mean squares, and then the F statistic, right? Now, sum of squares between is what we calculated here. Sum of squares within is what we calculated there. And the total sum of squares is what we have here. Our degree of freedom was the number of groups. So we said the number of groups for the degree of freedom for the between sample is K minus 1. Okay, K is 3, right? So we have 3 minus 1. That gives us 2. And then the within groups is N. N was 15, right? 15 minus K. K is 3. So we have 12. And of course, our total will be 12 plus 2. That gives us 14. Then we need to find the MSBs. The mean squared is just the sum of squares divided by their respective degrees of freedom. So we have this divided by the degree of freedom. We have that divided by the degree of freedom. We don't need to calculate MST. There's nothing like that in the analysis of variance. Then the next one we do is to calculate the F statistic, which is this divided by that, the MSB divided by the MSW. That gives us the F statistic. Okay. Before I move on. All right. So, Michael, did you have a question?
No, please. I was telling you that we are moving too fast. Some of us, we are chasing the numbers to get what you are doing exactly.
Okay.
But you were flipping the pages right and left, and I was a little bit confused.
Okay.
So I was drawing your attention to it.
Are you okay now?
From your calculation, I think we'll just have to go back to the slides.
All right. Okay. I'll check back with you later. All
right. Thank you very much.
Hello.
Yes.
Please, my question is about the SSB. Why we are multiplying the total by the 5. I don't know if we did that for the first one we did in Excel.
Yeah, the first one we did in Excel, we multiplied it. We weighted it by the sample size. If you can see here, it's 5 times what we have here. Okay. All the SSBs we calculate will be weighted by the sample.
Yeah.
Remember that in the determination of the SST and then the SSW, we use each of the numbers each of the values, so we didn't have to weight it by the sample size because each of the values were used. But in the determination of SSB, we are using the averages, so the average for each group. So you need to account for the sample size that you've not used. Okay.
Okay.
And accounting
Yeah.
for it,
Thank you.
multiplying by the n. So when you are determining or you're calculating the SSB, you should always weight it by the sample size. Now, for this question, we didn't, it's, we weighted it by the sample size, but because it is the same across board, it's 5 for group 1,
Yeah.
group 2. It's easy for us to bring it outside so that we can
Mm.
do equations and solve what we have to solve. I hope that is okay.
Yes, please.
All right. Okay. All right, Michael.
So please with the SSV. So if you want to calculate the SSV, will you take, if I take club 1, I'll take each element then minus their respective mean squared, and I'll do it for club 2 with its mean and club 3 with its mean.
What am I calculating?
The SSW.
The SSW, right?
Yes, please.
So for the SSW, when you take club 1, right? When you take club 1,
Yes,
you take it from its group mean. So it's that the group mean
it's
for
group mean.
first group was 239, right?
Yes,
The second element in club 1 is 263. You take it away from its group mean, which is 249. You do likewise for all the elements within club 1, right? But when you come to club 2,
right.
take its first value and subtract it from the second group mean instead.
Right.
Do you get it? Then
Yes, please.
218 second group mean, 235 second group mean, and so on until you are done. Then you come to club 3, it is 200, the first value, minus the third group mean. Okay, so
Yes,
calculating the SSW, it is all about you taking each of the individual values and then their respective means. This time it's not the grand mean. The grand mean is when you are calculating the SST, when you take each of the values from the grand mean. When we are calculating the SST, it's each individual value from its respective group mean. I hope that is okay.
right. Yes. So
Yes.
please, if you raise the MSB and MSW, the 3 minus 1s and the 15 minus 3s, are they the freedom of something?
The degrees of freedom, I will explain them.
The degrees of, all right.
Okay, Anthony, yes.
So my question is that how do I get the 5 in front of the SSB? Because in the first data we had 5 in front of the SSB. So my question is, how do we get the 5?
How do we get the 5 in front of the SSB?
Yes, I understand the whole data, but apart from the 5.
No, if you check the what I said, the SSB is calculated by the mean, the difference between the respective group means from the grand mean, right? And it's weighted by the sample size. So
Okay.
actually, the 5 was the sample size of the various groups. You get it? But because each group had the same sample, it was easy to bring it outside.
Yeah.
You get it now? Okay.
Thank you, sir.
All right. Yes, any other question? Michael?
Say,
Yes.
please, I've lowered my hand. It's something I'd wanted to ask.
Okay, yeah, I think these are very good and legitimate questions that you were asking. So that's very good. So once you've been able to get these things, you can easily find the test statistic, and this is how the Anova table would look like. Yeah, this is basically how the Anova table would look like. Okay, and I think we have done that. We were up to the point where we calculated the F statistic, right? Let's come here. Yeah, we calculated the F statistic. Now we need to determine the critical value of F. Okay, the critical value of f. And the critical value of f is such that I think I indicated it somewhere here that it's f alpha k minus 1 n minus k, right? Now this question says that our critical value, our first degree of freedom is 2, k minus 1 is 2, n minus k is 12. So you have f 0.05 0.05 to then 12. Okay. This is not 1. It happens to be my comma, but screenwriting. All right. So basically, that is what you're going to look out for. So you're going to search for this in the F distribution table. Okay. So when you go to the F distribution table, this is what you have. Make sure that you are looking at a significant level of 5%. Numerator degree of freedom is 2. Denominator degree of freedom is 12. And they coincide at a value of 3.89. So our critical value is what? 3.89 or 3.885. Then the question is, the decision rule is that you reject the H naught when, of course, the test statistic is bigger than the critical value. And the test statistic of 25.275 is way bigger than the critical value of 3.89. Therefore, you reject alpha at 0.05 and conclude that there is evidence that at least one of the means differ from the rest. We also have Excel approaches to solving this, but we are not going to handle it for today. I think we will deal with it in our next meeting. All right, so I think this will be a good place to end. Thank you so much, and we'll meet next week. Any questions? Okay, so we continue. What we are left to do is, the results of the Anova test, if we reject the null hypothesis, it just tells us that there is a difference, okay? But it doesn't tell us where the difference is really coming from. So for instance, for this question, if you look at the null and then the alternate hypothesis, we indicated that the null hypothesis says that all the means are equal, but the alternative hypothesis says that at least one of them is different, right? Not all of them are equal. So what does it mean? What it means is that it's either mu1 being different from mu2, or mu2 being different from mu3, or mu1 being different from mu3. The results of the hypothesis test doesn't tell us where the difference is coming from. It just tells us that there is a difference. But we are also interested in identifying where the differences are coming from. Okay, so how do we navigate this? Where do we continue from when we are faced with such a situation? So once there is a conclusion that there is at least one of the means are different, we should be able to identify wherein lies the difference. Okay, so that is basically what we are going to do as far as this analysis of variance is concerned. So we are going to go through a certain procedure, which is really part of this whole analysis of variance thing. And we there are so many ways to do this, okay, but we are going to look at one or two procedures for identifying which of the populations are significantly different, okay, and we call it the Tukey-Kramer procedure. The Tukey-Kramer procedure. Those of you who are familiar with pronouncing U as A, I don't think you can pronounce this one as Taki, right? But we will call it the Tukey-Kramer procedure. And what it does is basically to tell us which population means are significantly different. Okay, which population means are significantly different. So is it that mu1 is significantly different from mu3? Is it that mu2 is significantly different from mu3? And so on and so forth. Now, for us to do this, okay, we will be doing what we call pairwise comparisons. So we will take each of the group means 2 at a time. Okay, so we are going to undertake pairwise comparisons to see where the differences are coming from. And when we do that, we are going to calculate what we call a critical range. Okay, a critical range. And that critical range is going to be obtained from this relation that we have. Okay, the critical range is going to be obtained from this relation. And this is the relation that shows that it's take it as a test statistic that you are calculating. Okay, so we are going to have Q alpha. This Q alpha is obtained from another statistical table that we call the Q tables. You're not going to go through the Q tables. I'm not going to read the Q tables for the purpose of this class. If there's a need for you to use this procedure in an exam or in whatsoever it is, you would be provided with the value of the Q, or you will be provided with a Q table. I mean, it's really it's read as you would read from an F distribution table. So there is nothing much difference from reading Q tables and then F tables. Actually, it has K and then N minus K degrees of freedom. So it is the same thing that we've been doing over and over again. All right, then of course we have the square roots, the mean square to error divided by 2, then 1 over Ni, that is the first, the sample size of the first group, and then 1 over Nj, the sample size of the second group. So we're going to take them two at a time, okay? And we're going to calculate the critical range. Now, when we calculate the critical range, so this is how the Q table looks like, okay? It's the same as, how do you call it? It's almost the same as that of the F table, numerator degrees of freedom, denominator degrees of freedom, and so on and so forth, right? When we calculate the critical range, what we are going to do is to compare that value with the absolute value of the differences in the sample means. I'll take it again. We are going to compare the critical range, okay, with the absolute value of the difference between the sample means for the 2 points, that the 2 groups that we have selected at the time. Okay, now when you compare them, okay, you would compare the critical range and then the absolute values. Okay, now when the absolute values are greater than the critical range, then it means that there's a significant difference between each pair of the means. We will take the example one step at a time, so don't worry about it. But if it is small, then we will conclude that there is no significant difference at a go. Okay, so that is what we are going to do. So let's look at this example. I think you remember this example that we had. So we had the 3 golf clubs, and we wanted to find out whether the club actually made a difference in the estimation of the distance that it travels, right? So did the club matter? And we were asked to find whether there was a significant difference in the distances that are traveled, the average distance that are traveled in terms of the various golf clubs. Okay, and the work we did, we came out with a conclusion that there was the evidence that at least one of the means are different from the rest. Okay, so our conclusion favored the alternate hypothesis. And so the next question we want to ask ourselves is, where is the difference coming from? Okay, where is the difference coming from? So in order to find that, we first have to consider it on a pairwise situation. When I say pairwise situation, you take the sample means 2 at a time. Okay, so I'm going to compare club 1 and club 2. I'm going to compare club 1 and club 3. And I'm going to compare club 2 and club 3. So imagine there were 4 groups. Then I would have compared club 1, club 2, club 1, club 3, club 1, club 4, club 2, club 3, club 2, club 4, club 3, club 4. Right. So the more the groups, okay, the higher the number of pairwise comparisons that you would have to do. I hope that is okay. So you have only 3 clubs. So we are just going to compare them pairwise, and we are just going to have 3 pairwise comparisons. So club 1 and club 2, club 1 and club 3, and then club 2, and then club 3. Basically, that is what we are going to have. So when we have that, we would just continue with what we are doing. So we're going to take the absolute mean differences. So when I consider club 1 and club 2, okay, when I consider club 1 and club 2, I am going to look out for the difference in their sample means. Okay, so club 1 had a sample mean of 249. Club 2 had a sample mean of 226. Okay, so I look out for 249 minus 226. That gives me what? 23.2. Now remember that I'm not interested in the sign. I'm interested in the magnitude. Okay, so the absolute value of the sample, the difference in the two means. So I compute the difference between club 1 and club 2 and I get 23.2. I compute the difference between club 1 and club 3 and I get 43.4. Okay, that is 249 and then 205. Then I compute the difference between club 2 and then club 3 and I get 20.2. And those are the differences. Right now, once I have these absolute differences, I'm going to compare them with what we call the critical range. Okay, we're going to compare them with the critical range. So it is based on the critical range that would help us to do the other things that we want to do. Now, the critical range formula is giving us the MSW divided by 2, 1 over Ni, and then 1 over Nj, right? For each pairwise comparison, you are going to calculate a critical range. Okay, so between club 1 and club 2, you will calculate the critical range. Between club 1 and club 3, you will calculate a critical range. Between club 2 and club 3, you will calculate a critical range. Okay, so, but because the sample sizes, I mean, the MSW is what we recorded in the, if you check the analysis of variance that we did, we had an MSW of 93.3. So we're going to use that. But the only thing that differs in the calculation of the critical range for each pairwise comparison is the sample size. So what it means is that if the sample sizes are the same across all the groups, then you're just going to have one critical range to use for all the comparison. So in this particular instance, we don't necessarily have to worry ourselves in calculating 3 critical ranges, okay, for each pairwise comparison. We just have to calculate only one critical range because the sample sizes are the same. Okay, so what we are going to do, we already know our Q alpha from if we had to read from the Q tables. Okay, this would have been the value of the Q alpha, which is 3.77. and we put it in the square root sign. We have the MSW, which we calculated in our earlier solution when we were doing the analysis of variance. The actual analysis of variance. We calculated it. We had 93.3. You divide it by 2, and then you we have the sample size is 1 over the first sample plus 1 over the second sample, and you solve, and then we have 16.285. 16.285. So what it means is that the critical range is 16.285. Now we are going to compare this 16.285 to each of the pairwise comparison. Richard, I will get back to you soon. Okay, we have 16.285. I'm going to compare it with these pairwise comparisons, and what is going to happen is that when you compare group 1 and group 2, the absolute mean difference is 23.2. Okay, now this 23.2 is bigger than the 16.285. That tells you that there is a significant difference between group 1 and then group 2. Okay, then also if you compare group 1 and then 3, we have 43.4. Okay, that tells us that there is also a significant, if you compare that to the 16, this 43.4 is bigger than the 16. So group 1 is also significantly different from group 3. Then when you look at group 2 and 3, it is 20.2, and the value is, we are comparing with 16.285. So 20 is bigger than 16. So that tells us that group 2 is also significantly bigger than group 3. So when you really check, you realize that the mean for the first group, right, is not the same. It's not the same as that of the second group, right? And also it's not the same as that of the third group. Basically, that is basically what we are saying. So all of the absolute mean differences are greater than the critical range, right? They are greater than the critical range. Therefore, there's a significant difference, right, between each pair of means at the 5% level of significance. Okay, Richard, your hand was up. I think is that the one? Yeah. All right.
Please, I wanted to know how you calculated the 93.3.
Okay.
I mean, how did you get the 93.3?
No, we already calculated the 93.3. That was the MSW we calculated. You realize that in the earlier solution, when we were doing the Anova, right, test, we calculated the SST and then the SSW, right? And in the Anova table, the SSW divided by the degree of freedom give us the MSW. Okay, and that's the 93.3 that we are using. So that is basically how we did it. Remember that the relation for the critical range is actually MSW divided by 2. So the MSW is what we picked from the Anova table. I hope that is okay. All right, Michael. Michael.
Hello, sir.
Yeah.
Please, how did we get the 3.77?
We read it from what we call a Q distribution table. If you do not have the table, let's say in an exam, if we do not have a table, right, we are going to be provided with that value, okay? But the table can also be given to you to read. So basically, it's just like reading from a normal statistical table that you know. It's the same as reading from the F table, the same as reading from the standard normal table. We also have a special table that we use to read this, which we call the Q distribution table, right? So you read the degree of freedom. I think we have a sample here. Okay, it looks like this, having k degrees of freedom, k, and then n minus k degrees of freedom. So you see that here is our k, right? And then here is our n minus k, which was 12, right? Then when you read, you get 3.77. So that's how we got that value. Okay, Maureen.
Please, you were saying something about the NI and the NJ. I didn't really hear you well. Were you saying that because the population for each of them, the sample sizes were 5 for each, that's the reason why we just did the critical range once?
Exactly. So ideally, if the sample sizes were different, we would have done different critical ranges, right? We would have used 3 different critical ranges for each pairwise comparison that we have. Okay, but this is the situation where we have each of the samples having the same size. So each of them will have the same critical range. That is why we use that. Okay. Yeah.
So please.
Oh, sorry. I think you should come again. Sorry, you are muted. Yeah, Maureen, please come again. Yeah.
Yes, please. So in that case, when we have to compare, if the samples are different and we calculate the critical ranges 3 times, how are we going to do the comparison?
So you see that the comparison between x1 and x2, s bar 1 and s bar 2 would have its own critical range. Okay.
Okay.
You're going to use that critical range. x1 and s3 also have its critical range. You're going to use that, and then x2 and s3 also have its critical range, basically.
Okay.
All right.
Thank you.
All right, sure. Grace.
Sir, please, the k, please, which one is the k?
Oh, the k is the number of groups. So
the number of groups.
So we have 3.
And n is?
N is the sample size. So big N is the overall sample size. That is the number in group 1 plus the number in group 2 plus the number in group 3. So if you count all of them, you have 15, right? But, and the NIs are the sample sizes in each group. Okay, so this like N1, okay, then this like N2, and then you have N3, basically. That is what. Right. Okay, sure.
I wasn't what you said the k meant. Sorry, please could you go over the k?
But the k is the number.
I forgot what you said. Number of degrees. Okay.
Number of groups. Groups. Yeah. All right. Okay. So I think that is basically what we have. Okay. So we have 3 groups, 3 independent groups, populations. So group 1 for club 1, for club 2, and then for club 3. That is what we are using. So if there are 4 groups, then we have we have 4 k is equal to 4, and so on and so forth. All right. We also have another way to do this test, just like the Tukey-Kramer approach. We call it the Fishes Lsd Test, right? It's the same way that we are going to do. The only difference is it also allows pairwise comparisons and so on and so forth. The only difference is how the critical range is calculated. Okay. When we are using the Fishes Lsd test, instead of using a Q table, you're going to use a T distribution. And that T distribution will have n minus k degrees of freedom. Okay, so instead of using a Q distribution for the Fishes Lsd test, we're going to use a T distribution, and the MSW will not be divided by 2. So the only thing that differs is just the way to calculate the critical range, but any other thing is the same thing that you go through. Okay, so the same thing, then you compare and contrast, and then that would be what it is. Any other question with what we have for this? Any other question? Actually, this test brings us to the end of analysis of variance. So if there are no other questions, we would gladly move on to what we have to do for today. All right, any questions?